You haven't taken a papaya out of the fridge, Soggy?
Oh, man.
I think it's still good.
Still good? Okay.
Yeah, actually. They last a while, yes.
We're doing okay. Just setting up for SimPEG meeting now. It's always challenging without Lindsay, so we probably need you.
I'm pretty sure you can manage
One moment. Very organized.
Hey guys.
This is a good opportunity to practice. No?
Wow, Joe the Beard.
Yeah.
Hello.
Hello. Hey Joe, how's it going?
Oh, sorry.
How are you?
Doing all right?
Can you hear me, Lindsay?
Yes, I can.
Yeah, you can hear us.
Okay.
Oh, you can't hear. They can't hear us. This happened last time.
Oh no. Said to make sure my video was working before.
Hello.
Hey,
Hello.
Soggy.
Oh, there we go.
Can you hear us?
Oh, yes.
Wonderful.
Well. Oh, it's very hard always. I'm just like progressing, Lindsay. It's just.
Well, I'm glad you got it sorted.
Yeah. With help.
How are things going?
Okay.
Yeah.
It's pretty quiet. But that's fine.
I like the beard, Joe. Looking good, man.
Thanks. Now that I don't have to keep it shaved for a wedding or anything, might as well try.
Now that you're husband, you can do whatever you want.
Yo.
Wow, that's.
And how's your summer been treating you?
How's my what?
Summer. I guess it's sort of
Oh.
spring.
It hasn't even started yet.
Oh yeah, fair enough.
We're just finishing up everything for the semester, and then on Sunday I'm leaving with the field camp to go down. We go to Pagosa Springs every summer, so
Okay.
it'll be nice.
Well, that's good.
It'll be a nice 2-week field camp, a little break. So that usually is what kicks off the summer. Got to take care of 40+ undergraduate students.
What's your status right now, Joe?
My status?
Yeah, at mine.
Hopefully, I'm still a PhD student, but should be finished in December. Like I should graduate in December. So.
Hey, Rowan.
Hey. I only have 10 minutes, but I will definitely watch the recording of this.
Sure thing.
All right. Soggy, have you started recording?
I think so.
Yeah. I think
Yeah, we're recording,
We're
right?
good to go.
Yeah, we were recording before.
Okay. Perfect. Well, do you guys want to jump into things a bit here?
Yeah.
Sure.
All right. Well, Joe, I think we'll let you take lead if you're game.
Yeah, sure. I can do that. So this is something I've been working on off and on for about, I don't know, 6 months to a year. When I've had time, I sit down and just kind of something to distract me from other things I was doing. And it kind of motivated because the tree mesh object creation has always been kind of slow compared to what it could be. It's really, really powerful once it's been constructed, but it just always lagged. And I was just kind of like, what can I do to fix this? So, like I said, it was just a fun exercise in coding and seeing what I could do. So just let me show you a little bit about what's improved and how fast the creation is right now. share my screen.
We can almost see your screen through your glasses if you really work hard.
Yeah. Okay, here we go.
Augmented reality.
So this is, I have two environments set up, one with the old style, the old tree mesh, one with the new one. So just as an example, this is to show you guys that it's doing the same thing, or at least setting up in the same way. So I have a simple function that defines how it's going to be created. Like a fresh kernel here. So this is a pretty small mesh, right? Like there's only 8 of them. This is the old one as well. So there's only like the base tensor mesh would only have 8 cells in each direction. So it's still a pretty small mesh. And this is what the grid would look, the mesh itself looks like, right? There's nodes. Before we define these nodes as hanging, but what's really happening is that there's 2 nodes plotted on top of each other right there, right? There's one that's non-hanging, one that is hanging above it at a different level. It kind of creates a little bit of confusion here. So let me do the same thing on this mesh. So this is the new version that I'd written. A little bit, so just to keep it simple, there's only a refine function at this point. There's, from what I understood, hasn't been very common to use the coarsen function at all. I don't know if any of you guys have ever used it in your coding. If you have, you can correct me, but I don't think I've seen much use of it being used outside of testing that it worked. So if no one's actually using it, I didn't feel like supporting it at this point.
Mike, is that something you've used?
No. I've done most of my mesh generation outside of SimPEG with the UVC stuff, and then just pulled in, just read in the meshes mostly.
Mm-hmm.
But can you coarse it in UVC?
That's a good question. I don't think so.
Okay. Yeah. Sorry to sure. Go ahead.
It seems like something like, I mean, nobody really ever used it. It's just there is something that could use. So it does. So even for this small little mesh, so this one took the fast. My new implementation took 1.35 milliseconds. This one took 22.9. And most of that is just other calls going on behind him. But still, that's about 20 times faster right there, even for this little guy. But it doesn't make that much of a difference because it's small mesh anyway. The biggest difference here is these nodes. So in the implementation now, every node is only at one location. There's no such thing as, the nodes are not identified by which level they're at. Instead, they're just identified by where they are in space. And it ensures that they're unique nodes. So the only hanging nodes that really matter are the ones that are on these hanging faces. But so the nodes are the only thing, the hanging nodes are the only thing that really ends up differently, because as before, I said hanging nodes happen when they're at different levels. But now there's not a concept of a level associated with a node, it's just a location. Here, generates the same faces, and it would generate the same Y faces as well. Another thing is I've implemented most of the edges in X and Y as well for a 2D mesh. Just they hadn't been implemented previously, so I was writing it. I might as well have done it. So anyway, that's just kind of, you guys see that it's doing the same sort of stuff. Now let's keep it in 2D. Let's go up a few. 128 cells in each dimension. Okay, that one took 2.9 seconds. 122 milliseconds. So it's just, from what I've seen, the factors, it's about 45 times faster construction itself in 2D. And in 3D, this will take a little bit of time, but still 128 cells.
Okay.
So this is the fast version. Should finish pretty soon. Yeah, 8 seconds. 50 times in 3D, I've seen it's been about 50 times faster. So I'm not even going to run this one with this size over here because it'd probably take about 20 minutes to finish.
Oh,
Nice,
wow.
nice, yeah.
That's great.
So, or 10, 20 minutes to finish. So I can at least do a little bit slower here, a little bit smaller. This is the slow version of the old style. So 6 seconds. It's weird.
That's pretty good.
Yeah. I don't know why it took a little bit faster that first time, but there, see, it's about 151 milliseconds as opposed to 2 seconds.
Can you visualize the mesh for the 3D as well?
This one will take a little while.
Oh, cool.
So that's one level refinement. I saw in your notes that we can't recall the refine one more than one time. Is that right?
At this point, yeah, there's no reason I couldn't support that. I just hadn't thought about doing it yet. It wouldn't be that hard, honestly. Let's go smaller so we can see what it's actually doing on this.
So Joe,
Yes.
is there a really special environment that this is going to work, or in most machines it's just going to work?
I have it on the testing. Well, it's worked on all the testing environments. I finally got that going. So it's on Windows. It's on Linux. This is running on my Mac right now.
Okay.
So I've seen all these things working already.
I got a crash yesterday, actually, on Windows, but I think it was a C++, another C++ thing, and I'll bump the crash to you after, if you don't mind.
Yeah. So, I mean, there's still probably bugs in it that I haven't caught. Just because I haven't tested it with everything that everyone else has used. I'm not actively using a lot of the tree mesh stuff, and anything I'm doing is just a fun project that I was working on. So that's why I was hoping that if it could get pushed down a little bit more, broken and tested a little bit more, I could hopefully find more of those little bugs that are in there.
Yeah, that'll be great.
I'll get on it for sure, man. We'll use it.
Yeah.
How about the order test in SimPEG test? Is that passing?
Every test passes that I've done with. So I've on the pull request, I've essentially replaced these two. I had to turn off a few tests for things that weren't implemented yet.
Okay.
But all the order tests passed. The tests that I had to turn off were testing that had to deal with the properties class.
Yeah.
So that's another thing that is not necessarily super supported like that, is the properties class, because I don't have as much experience with that.
Right.
But another thing is the operator construction. So let's see, I've got this 8x8 cell here. So it's still pretty quick.
Did you manage to salvage the stencil operators?
Kind of. I was able to salvage the cell grad operators, and it's just I'll get to the code in a sec, and you guys can see what's happening and what's changed.
Let's do it.
So this was one of the meshes that Michael gave me. So this is the old style. This mesh took about that long to create and read in. So now, and then to create the phase divergence operator for this mesh, I'm not going to do it right now, but you can see it took me on my machine 2 minutes and 42 seconds.
How was it before, Mike?
But that's it.
This is
I think it
this
might
is the old version.
Yeah.
Okay.
Oh, I see. I see.
In the new one,
100 milliseconds.
I'm going to read in the same mesh here. I'm going to create the same phase divergence operator.
That's so good now.
That's pretty good.
Yeah.
So it's
Wow.
even noticeable. It's even more noticeable with larger meshes,
Yeah.
especially the operator creation. It's just,
Ah.
I mean, that's over 1,000 times faster.
Whoa.
And I guess the more complicated the mesh is, right, the different changes and tree levels and everything, that will speed it up.
Right.
Ah.
So there's a lot of little things that I've implemented in the mesh that are kind of like exciting little changes and different things. So I'm going to show you. Let's look through some of the code as well. But this is kind of this kind of gives you guys an idea of the speed ups that can happen from it, and now I'll show you how I do that. Oh.
And that's how you do it, out of your brain.
Sorry, it's on a different desktop. Okay, so the idea here is that let's start from where it's going to get, where the function gets entered into. So not tensor mesh, tree mesh. So this is just the Python code that gets called. So I'm inheriting a tree, this underscore tree mesh, which is what is defined. This is the class that's doing that's doing all of the work basically. And then I'm inheriting the other classes that you'd normally expect. There's not too much implemented in this high level version of it here because most of the stuff is in Python below it. There's just a few simple stuff. So the cell grad, this is essentially copied right out. So this thing still worked exactly how it did before. I'll talk about averaging, or the averaging construction in a little while. Okay, so this is the Python file that's controlling all of the underlining. This is a Python file that's controlling all of the underlying code. So there is a little bit of magic here that happens in order to call a refined function that is just defined in Python. I need to actually call that Python function all the way down to the C++ code that's building the tree. I need to call a Python function from C++.
Okay.
So one of the ways that I have to do that is I'm defining a C-defined class. So Python you can define classes, like Python classes like you would. You can also define define Python extension classes using the cdef statement. And these classes are closer to what you would expect from like a C or C++ type class where they have members. They don't have, the biggest difference is they don't have dict objects like you would expect a Python class to. And that makes the lookup of objects in the class faster. But you can also you can't add items to it after it gets created. So with a Python class, you could add an attribute later and it would just add it to its underlying dict of objects. Well, you can't do that with these C-defined classes because, like, as a choice for these methods, it makes it faster not having to go look up that dict object. So this class here is just a cell. So this is kind of what's the first level of switching between the C++ code to call the Python code underneath. I've given it a cell, which I've defined in C++, and it calculates all of the normal values that I would expect. So this is essentially going to look and work exactly like the cell used to in the current implementation of tree mesh. It has all of these same properties. So the functions, the refined functions that we were using before should still work on this. Anyway, and then I have to define a little function that wraps whatever function you would give it, calls the cell, and returns the function. So you see a little bit of casting going on here. So this Python function needs to get cast to a Python object. And then I construct one of those cells and call the function and cast its return type. That's the basic working of how the C++ code calls the Python functions underneath. That's not as exciting as the whole tree mesh. So like I said before, you can't add members to a class after it's constructed, a C-defined class, a Python extension class. So you have to define every object beforehand. So this is essentially all of the cached things that we would normally expect. I just have to define them ahead of time. And then when it gets initialized, I set them all to none. So the tree mesh, when it gets constructed, initializes its base tensor mesh, and then initializes the underlying tree mesh, which comes in here, does some magic to set its max level, determine the locations of the nodes, like all the possible locations of the nodes, meaning the X, Y, and Z defined by indexes, I, X, I, Y, I, Z. And then we do some initialization of the tree in C++. And then when we want to refine it, goes through here, it wraps the function, and then builds the tree, as well as numbering it. The tree is built in C++. So one of the nice things about Python then is that it's easy to wrap C and C++ code. So this is the C++ header file to kind of give you guys an overview of all the things that are implemented in it. If you're really interested in the exact details of what is going on, you can look through the functions. But the big takeaways here is I define these two key functions. So each node and each cell, each face, each edge has a location defined by its dimensional indexing. So I, X, I, Y, Z. This key function takes those numbers and uniquely maps it to a single integer. So given an integer X and Y, it'll map it to another number that is unique. So this ensures, as I'm creating them, that I will only ever create one node or one edge or one face at a single location. I use this key function first to see its value. All of the nodes, edges, and faces get stored in a map, which maps that key to a node. So if I ever wanted to create a node in the mesh, I would first check this map to see if it was already in it. If it was, I would grab it. If not, I would then create a new node and return that. So this is what ensures that nodes are, like how I said before, their nodes are specific to a location. There's no concept of this as a level before.
Just a quick thing, Joe. Some people might not be as familiar with the map terminology. Is a decent mental model of that thinking of it as like a simple dictionary, basically?
Yes, it's essentially a dictionary object. the key here is that it maps a key value to some other object or some other thing. It is a unique, you can only have one object per key. Each key refers to only one object. So that's how this map works. And this is also an ordered map. So they're ordered by their key values, meaning if I wanted the time it takes to look up a certain node based off of its key is small because they are ordered. It doesn't really matter how they're ordered. It's really up to the map implementation to determine the ordering of the objects. The idea here is that the nodes are all stored in a map, as well as the edges and faces, uniquely. So now let's look at what a node is. A node has its location index, so IXIYZ, its location in space, the key value, a reference. So this reference is something that I use to keep track of how many times it's referenced by other objects. Its index, so this would be its location in that array that you would use to, in the higher C+ and Python files to, like this would be either the column index or a row index, depending on the matrix that you're building. Every node will also know whether or not it is hanging. And then if it is hanging, it will define parent nodes. So this kind of leads to the fact that each object is aware of what is around it, or it's aware of the structure of the mesh. So it has parents. So each node, if it was hanging, it'd be able to know its parents, which would make the deflation matrices easier to build.
Yeah, that's exactly what we need. That's perfect. Hey, I have a question. Like, it's not going to be an issue right now, but what's the maximum? Because if there are integers and we're a 64-bit system, so what's the largest
So
matrix we can pick up?
These int types are defined as a standard size t, which is the size of the pointer on the index that it's the size of the pointer on the machine you're currently using, or that you're used to compile this. So if it was compiled with a 64-bit processor, 64-bit G++ compiler, this int type would be a unsigned long. So this is the largest. This will adapt to whatever size you're on. So it'd be an unsigned 64-bit integer on a 64-bit machine, an unsigned 32-bit on a 32-bit machine. So
yeah, I don't know how much that is, but it's in the
yeah, I mean, on a 32-bit machine, that's 4 gigabytes, roughly, like 3 point something. And on a 64-bit machine, it's whatever that largest int type value is. I don't know offhand. Whatever 2 to the power 64 is, 2 to the power 64 minus 1. So that would be the largest size you can essentially handle in these. Now the key function. So I don't imagine any issues between 32-bit, 64-bit as far as storing a matrix size, because they're all implemented as these int types. Now, so in the Python file, let me show you how you can deflate the nodes really quickly. So because each node knows its parent and whether or not it's hanging, that makes the deflation matrix very easy to understand, at least conceptually. So we can loop through all of the nodes, get the node's index, assign the I index for all 4 of its parents, and then if it is hanging, I know all of the indexes because they've already been numbered. So I don't have to go about messing with a lot of those underlying functions to, okay, I need to get a node at a level above this and find the nodes around. Everybody already knows about it. That makes this construction very quick. And plus, all of these arrays are pre-initialized. So that's a big improvement just from the old implementation of tree mesh, is that most of these arrays are initialized and appended to. So that makes the construction a lot quicker. Now, a little bit of magic here that I figured out is in 3D, it would be possible to have had a node that had a hanging parent node. So it's kind of a weird thing to think about, but it would happen if a cell was diagonally adjacent to a cell that was 2 levels below it. There would be that's something that's balanced. Like, that's still considered balanced in the way that we've talked about it. But in that case, the way that my current implementation is that a parent just knows about the two, like the node just knows about its next level parents. You could think about it. And that kind of makes the construction a little bit weird to think about of this deflation, because each node is essentially the average of its 4 parents, or 2 parents in 2D, but in 2D it just has 2 parents repeated, so the implementation is the same. But something I figured out is that this deflation matrix, essentially, if the node is not hanging, it is just an identity matrix. And then if it is a hanging node, it's the average of 2 parents, right? Well, one of those parents could be hanging, the other could not be, or both of them. I don't think that it's ever the case where both parents are hanging. But either way, what you can keep doing is you can apply deflation matrix to itself. And eventually, that will get rid of all of the hanging parents.
And Joe, visually, this is the case where you have the node, like the hanging node, that's potentially in the middle of a face going between dimensions?
It's a hanging node on an hanging edge where 2 of the in 3D, there would be 2 cells that are diagonally, that share an edge, that could be 2 levels below, apart from each other. That's the only case where I've seen it happen. So the balancing only occurs between faces, right?
Right.
So the balancing doesn't occur along edges. So this just basically happens when essentially edges are not balanced, which is not being something that's being enforced.
Okay.
Which hasn't been it before. But this is just a quick way to take care of it. Otherwise, I would have to search in the construction of it. I just kind of kept it simple, but you'd have to essentially look for a parent. Okay, is that parent hanging? Then you have to look at that parent's parents and see what that is, and it just kind of gets recursive. And this way was just, once I realized I could do it this way, I just did that way and stopped thinking about the other way.
That's clever.
Yeah. And the same thing can happen with, that case cannot happen with the faces, because like we said, the faces are, like, all of the cells are balanced along their faces, but it can't happen with the edges. So here is my deflate edges, where again, you see that same kind of trick happening at the end. Okay. But again, because every object knows like its parent and its index, it makes it really simple to construct these matrices, at least to understand what's going on. And a little trick here. So let me talk again about these, the edges and the faces. So the edge, again, it knows its location, has its key, its reference, indexes, it knows its parents. The edge also knows which points bound it. You can imagine that would be useful for constructing things like the edge curl matrix, right? It acts from points to edges, or from nodes to edges. Similarly, the face object knows its edges, and it also knows its points, and it also knows its edges, which is useful for creating face divergence matrices. Sorry, this is, and what was I thinking? Either way, you can imagine that they have references to the objects that make it easier to construct the matrices you need. Let me look at, to show you that. So this is the nodal gradient. The nodal gradient acts from nodes to edges. So I can loop over all of the x edges, get its index, get the index of the points that are around it, or that are on both sides of the edge, get the length of the edge, and construct the matrix. So it's very straightforward. There's not a lot of, at least I think it's easier to understand what's happening here. So edges x, edges y, edges z, and then you deflate it. So you deflate those nodes. While I'm thinking about this. So unfortunately, the codicy or any of the code checks can't really look at Python or Python files to check for errors. So I kind of fix things as I come across them. So right there, it's like, oh, those. So that could be something else if anybody wants to work on. It's kind of going through and add spaces, switch around. Again, the curl matrix is easy, right? It acts from edges to faces. So because all the faces knew which edges are around it, it's very easy to construct this matrix. Or at least implement the construction of it. And it should be very logical to anybody who's looking at this code to be like, oh, this is exactly what this is doing. Whereas if you try to go and look through the code of the old implementation, at least when I first started looking at it, it was not as clear to me what was going on. Once I started really understanding it and doing it, I was like, okay, I get what's going on here now. But initially, it was just kind of odd for me to understand what was going on. Hopefully, if somebody's looking at this, they could be like, yes, obviously this is the faces, they're getting edges here, it's the volume.
Yeah, this is really transparent, Joe.
Yeah. Yeah, I just tried, as I was doing it, I was kind of made it a point to kind of keep an idea of what was going on. So you had asked, Dom, you'd asked about the stencils.
Yeah.
So I did have to re-implement them just because it's a little bit quicker doing it this way. And I could pre-allocate a lot of stuff. The idea, I basically followed the same idea that you had, and that was very helpful looking through the code and saying, oh, I get exactly what I need to do here.
Yeah, well, you know all the neighbors, right? So it's pretty straightforward now.
Yeah. So the other thing is the cells. So I didn't get to the cell object yet. So the cell, I need to have it remember its dimension. It knows its parent cell. So the cell one level above it contains it. If it has been split, it'll know all of the children below it, and it'll also know all the adjacent cells around it. So it'll know its neighbor's cells, which makes it easier to construct the cell grad stencil, because I can just look, okay, I want to look at a neighbor. There's a little bit of logic that has to deal when its neighbor is not a leaf cell. What I mean by a leaf is that if a cell has children, it is not a leaf cell. Only cells without children are leaf cells. I also keep references to all the points, edges, and faces within a cell as well. Great. So everything is kind of aware of what's around it. There's a lot of logic that deals with how cells are spawned, how they're divided, but you can kind of imagine that this function creates, if a cell needs to be split, this function will create children. It'll also set up all of the, it'll create the children. And then divide will basically tell it, this is the function that you would call to recursively divide a cell.
On the boundaries, are those just like a neighbor is none in that case?
Exactly.
Okay.
So as it's initialized, so let me show the very base part of the tree here is where are you at? Okay, so I insert a cell. Let's look at the cell constructor. So whenever a cell gets created, all of its neighbors are initially null. Then I have to, and all of its children are null. So if cells are on the boundary, that neighbor will never have been set. So the neighbors only get set when things are created. So if you create, in 2D, if you create 4 children, you can imagine all the children, you can imagine one child is the neighbor of another child, and they both get paired up like that. However, if in each direction. But if you keep recursively doing that, it will never assign boundary neighbors to be anything except null. So that's an easy way to identify whether it is a cell has a null. If the cell's neighbor is null, that meant it was on the boundary.
So Joe, with that, like finding boundary cells or boundary faces or edges is going to be pretty easy here.
Defining the boundary cells and faces.
Yeah. Let's say you got a 3D domain. I want to find the boundary cells or boundary edges or boundary faces. Is that going to be easy?
They're not really listed like that. I mean, I haven't done that. I am trying to imagine how I could go in that. I mean, besides looping, you mean besides looping over all the cells and just saying if they're on the boundary? Because that's that's the easy way to do it, right? Just loop through the list of all the cells and determine if they have any null neighbors, or determine if a face is on the boundaries, determine its location if it's on the boundary. I guess the easiest way to do that with any.
Okay.
I mean, I could define a function that would give all of them, basically by always going to the outer cell of each division. So I'd start at the root cell, which is just one large thing. Look at the parent or its children, and then look at those children's boundary cells, and you can at least get a list of all of the boundary cells. But
yeah,
I haven't implemented anything like that, so it wasn't really something I was concerned about. And if you want, you can implement it yourself, hopefully, because the logic is clear. But yeah, it's just with the C++ code, if you're looking through it, there's a few things that are not as clear as the Python code, particularly when it comes to finding hanging faces and hanging nodes. I use a lot of little bit shift operations to reduce the duplication of code. So just like the little bit shift operations that depend on which node of a hanging face was not a hanging node, or which node of a hanging face was the center of a parent face. So because of those map functions, it's easy to find those values in So here I'm processing the hanging X faces to find those hanging nodes and hanging edges. You just loop through all the faces. If a face was on the outside here, it's by definition, it's not hanging. So I just skip those. But what's happening is I'm looping all the faces, and I have this reference here. This is what I'm using to determine whether to even check if it's a hanging node. So if the same face, meaning that it has the same center location, is referenced twice, it is not a hanging face. That means that it was part of two cells. Same two cells shared the same face. So then if it was not, that means that it could either have been a parent face or children, or a child face. I have left the parent faces as not hanging. So this is what happens here, right? If the face had a node at its center, that meant it's going to have children faces. So I'm saying that is not a hanging face. No, there's just a lot of operations here. So I find my parent. If I was a child, I find my parent node or parent face. And like I said here, this is kind of the least clear bit about what's going on here, that I'm using a bunch of bit shift operations to come up with these patterns. So this one would be, so the possible values of this IP parameter are 0, 1, 2, or 3. And this is the corresponding pattern that it comes up, that this bit shift operation comes up with. So 2, 0, 2, 0, it's just dependent on the ordering that I had the points and faces. So if you change the ordering of the edges, these have to change. It's a little confusing, but if you're really interested, I can talk more about it and why I did that. What else did I want to talk about? I was thinking about something else. So again, oh yeah. So after everything gets created, I've never assigned an index to anything. So to make it easy, this is how I number. I'm numbering all the nodes here. I loop through all of the nodes that are in the map. If it's a hanging, I assign an index depending on the hanging index. And if it's not, I assign it an index. The idea here is that all of the non-hanging nodes are indexed first. Then all of the hanging nodes are indexed. And the same thing happens with all of the X and Y edges. This is another reason why it's a lot easier to construct these, the matrices. I can just, as I'm looping through all of the, an example here. Okay, as I'm looping through all of the edges here for this nodal gradient, if it's hanging, I just skip it. I mean, this operation basically if it's hanging and I skip it, this only works because this index II's, everything is labeled or indexed non-hanging first, and then hanging. And if it wasn't, I would have to define a matrix that essentially removed all of those rows from the output. This is just doing that automatically. In the current implementation, so on the edge or on the nodal gradient, you might see a deflation matrix on both sides here. One that would remove the hanging edges on the left, and one that deflates the hanging nodes on the right. So now I only have to concern myself with deflating the hanging nodes on the right-hand side.
That's really cool, Joe. In the previous implementation, we did have to hit deflation matrices on both sides. Is that right?
Yes.
Yeah.
Because the indexes were
Muddled.
not ordered like that.
Right.
You couldn't like if you right. It's just because there were hanging indexes mixed up with non-hanging indexes, so you just have to go remove all of them afterwards.
That's really cool.
Even if there wasn't anything in that row, its edge index for a non-hanging would still be after those that had hanging. So you had to remove them.
Okay.
Now you just don't worry about it. So the basic idea is that I don't want to care about how I'm indexing things. I just want to know what the index is. And it makes it a lot faster to construct these matrices, because before you have to go and calculate what the index would be for an edge depending on its level, its location. There's a lot of parameters that go into it. I don't want to care about that. I just want to know what the index is.
Does this get complicated if we introduce multiple refinements?
So if we introduce multiple refinements, so like I'm assuming you're referring to the fact that I've said that you can only refine it once right now.
Yeah.
The only reason I only have it refined once is that this function here that creates all of the edges and faces and creates all the hanging stuff is in this function called finalized lists, which for some reason, when I was initially doing it, so if I want to build tree from a function, I go to function, and at the end of it, it finalizes the list. So actually, what I probably should do is remove this from here, and instead move it into the refine. Maybe there's an argument here, finalize. And this would have an option here. So if I set this as false, I could keep calling refine. And this would fix that thing where, like I said, you wouldn't be able to unrefine things. So this function then would only ever create more cells. It would never get rid of cells because of the way it works.
Until the last call.
At the last call, you would still have to, at the last time you would do it, you'd have to pass it a finalized true. So, I mean, I guess I should probably just leave it this way.
Yeah.
If you didn't want to do that, right? Like.
So, okay, is that only a function, or we can send just a cloud of points in the build tree from function?
So it's right now it's just a list of, you could either give it an integer to refine everything to the same level. I haven't added specifically like, oh, I want to refine these cells yet, or a list of cells. So something that could be implemented later. I don't imagine it being an issue, especially since separating out this like finalized lists thing. It would just have to be once you're done refining everything, you would have to finalize the object before you could use it.
Because that's going to be the most practical use of it, right? Is that we send our odds point in the tree mesh and just refine around it, and then go for it, or topography or any cloud. Yeah.
Mm-hmm. I have implemented a little bit along those lines. So I have a function here called insert cell. What it does is given a point, it'll insert a cell into the tree mesh with a given level.
That's perfect.
Oh, perfect.
Yeah.
So yeah, that's what that does. I had to implement that, and it's actually a pretty simple. Once I did this, I was like, oh, a lot of things turned out being simpler than I thought they would have been when I first started doing it. I do that because it's essentially how I built things from how I read in the UBC tree mesh. I just read it in, convert it up to a bunch of points and levels, and then insert all of those cells into the mesh. And that creates it. Instead of trying to explicitly do a lot of things, it's just a little bit easier to see. And I can see that in the mesh input output class. So I'm reading a UBC mesh. I get the index arrays from it, the others, and then convert them to a list of. There's this other thing going on, but essentially I convert them to a list of cell locations and cell levels. Right now, this method was a private method, but it could certainly be a public one just as well because of how it works. It's very simple to understand, I think.
Yeah, that's probably all we need. We can do the mesh creators on the outside in pure in SimPEG, and then we'll just call that one.
Right. So, yeah. That just does what you want it to. So once, see here, look, I'm finalizing the lists. So it gave a list of, this function took a list of cells. I should probably add that in as well.
The cells is just like a random form, so I can put it in.
Yeah, it was just a list. It would be a 2D array of points. And this, I could probably rename this to something a little bit better. So that's the other thing. It's like there's a lot of little things that can be changed in the implementation itself. For renaming to make the little things here clearer, so on.
So for instance, for topography, we just do an ND grid, and then drape on topography, and then feed it to this.
And then set the level.
Set the level. So what does it do for to switch from the coarser to the finer, Joe? Let's say we say the finest level, we send a cloud of points for the finest level. Like, what's kind of the arc-tree augmentation rate? You know, does it skip 2 cells or 3 cells or as fast as possible?
So what's going to be the orientation?
No, like at what do you limit how fast the arc-tree level changes from one level to the other?
Yeah, so everything is automatically balanced. It's just.
Is the minimum balancing just like one refinement?
Yeah, it's
one cell refinement
right now.
And so presumably we could sort of customize that at some point?
Actually, yes, and I can show you exactly.
Cool.
I know exactly where I would do that at as well. It's this little check here. So if my neighbor is not null, and its level is less than my level. So if think about your being a cell, okay? If I need to be split, and my neighbor is below my level, then it also needs to be split. So this by default is 1, but I could definitely change this, right? Its level is 1 level below it as well. This would split that as well. This would cause that balancing to happen if they were 2 levels apart, or if they were 3 or 4, however far apart. You could definitely control this.
I see.
And if you did that, it would still, a lot of these the matrices, the operator matrices would still work because of the way I've defined that the deflation matrices. Remember how I had that recursive almost definition of them? So it'd still be able to build valid deflation matrices and divergence and gradient operators on those matrices as well.
So just correct me if I'm not understanding this right. So that would change the number of levels of refinement. So if I had one cell that was refined by 3 next to one cell that was refined by 2, and I triggered this, it would refine everything down based on the number of levels that we set there. So I guess the other question that I have is, say I refine, I want to refine around a source or a receiver location. So I define sort of which level that I want the refinement right around my source to be. But then I want it to refine maybe like, instead of coarsening sort of by one neighbor immediately, maybe do 2 neighbors or 3 neighbors or something like that. So it's actually sort of a smoother octree in a sense.
Right.
Would we accomplish that the same way, or is that sort of looking at like looping over more neighbors than just like neighbors at I?
So the neighbors at I are like, it's immediate neighbors. If I would do that, I would probably put that kind of information into the function that I'm passing it.
Okay, that's fair.
Right, because we could just we could pass the wire and then do like a radius around the wire, send a direction, and then just have more complicated the mesh constructors without having to change that function.
That's
right. That might be easier to happen in that kind of function.
Yeah.
Whereas this is purely to control. I'd rather have this purely to control balancing operations on the matrix or on the mesh.
That's fair.
Almost something that should be separate from that kind of thing. But a lot of the things are still the same. Max levels, fills. A lot of the numbering just accesses the size of the underlying object in C++.
Joe, this is like a Python file, right? Like,
yeah.
Okay.
So it's Python, and it's generating a C++ Python file, and that's important because I've never defined what this IT type is anywhere. But because Python knows that this is a map,
I see.
in C++, it knows the iterator to that map, which is what this is, and it knows the type of that iterator. So there's a lot of automatic type definitions that come from getting a C++ Python file, which is really nice. So this whole loop here is all optimizes down to C++ code, as well as all of those operator matrices, wherever they went. So this is all the grid stuff, exactly how you would think they're implemented like that. There's grids for faces, hanging faces, hanging objects, and non-hanging objects. Volume, area, edges, exactly how you would think they would be implemented. That's how they're implemented. And basically, in almost every for loop, pretty sure every for loop that I've implemented has no Python calls to it, which is what makes it so much faster than before. One, that it's implemented. So there's 3 factors that are making it a lot faster than before. One, that the index and the value data arrays for the matrices are allocated ahead of time. 2, I don't have to calculate the index of each object as I'm going through it. And 3, that I'm not looping in Python. So those 3 factors combine to create a lot of speed up for the operator creation. Few other things, yeah. So the Solgrad stencil, it was easy because it knows the neighbors and it knows its faces. Deflation. the averaging operators. So the simple averaging operators are the ones that are anything to, like any of the objects to cell centers are easy because everything is in a line, everything is aligned. So it's easy to construct the averaging. The EX to cell centers is easy to construct because the cell knows its edges and it knows which edges so it's X edges and it's Y edges and Z edges. Those are easy to construct. Same thing with face X to cell centers. Same kind of idea. It's easy to construct nodes to cell centers because every cell knows its nodes. These are matrices dealing with the inner product stuff. Again, it's easy to loop over because every cell knows its face. And now, this is the big part that I was kind of getting hung up from for a while, is just the general get interpolation matrix. It's easy to think about when it's nodes, when you're interpolating from nodes on a tree mesh. And that's just, it's so easy, I just implemented it really quickly. So you calculate the weights and assign those weights to values depending on each node. So for each location, I get its X, Y, and Z locations. And then I have a function that I can return the containing cell. This is a fast lookup because of the structure of the tree mesh. Every cell knows its children cells and its center. So what it does is it essentially compares the value to its center. And depending on which values are less than or greater than, it'll look into a child. And then it'll keep going until it finds the leaf cell that it is in. And so it's like a log n search to find the containing cell. That's a pretty fast lookup there. So the nodal interpolation matrix is easiest to think about. The other ones required a little bit more thinking than I had time to do. So in the meantime, right now it just triangulates the input points using a Delaunay triangulation, and then calculates the barycentric coordinates for each of the points. There's a little bit of logic that has to deal with if you're interpolating or extrapolating any points outside the hull of the tree mesh, or at least those points, which I had to think about for a little while. But essentially, it just projects any points that are outside the hull onto the hull to calculate the weights. So there's just a bunch of logic that has to deal with that. But in general, it's just, I think I called it lazy second order, because it would require a lot more thinking to average an arbitrary point to cell centers, because you have to check, okay, if it's a neighbor, it's a lot of logic that comes from the fact that cells can be different levels next to each other, and it's hard to determine which cell centers it should be weighted of. When I researched a lot of I was going through a lot of research papers, and everybody's just like, this is not a trivial thing to do. So, especially for linear interpolation like that. So I just kept it simple for now, and it's not as fast as it could be. It's still faster than it was, but just takes a little time. It takes more time compared to the objects that would happen. This is the only, yeah.
Yeah, because I think even like the UBC codes will only let you do interpolation at the finest level of refinement.
Mm-hmm. It's something to think about. Hopefully we can get some at some point in the future, but I just implemented it so at least it was second order interpolation matrices. Plot grid is basically the same, everything implemented the same. I draw the grid based off of the edges instead of looping through the cells and plotting cell points. It's a little bit cleaner in 2 and 3D. What else? Oh, this is neat. So instead of like, oh, I'm going to do grid CC0, grid CC1, grid CC2, I just expand the transpose, the plot commands to get the grid. Yeah, it's a little bit cleaner. Plot image is essentially a copy paste from before, except replacing the cell from what it used to be. Plot slice, I haven't implemented yet. And then here are functions allowing this thing to be pickled. So because there's an underlying C++, it contains a pointer to a C++ object that's doing a lot of the calculations. It's hard to pickle it. It's hard to get a serialization of it directly. So I had to implement some functions that would get a representative state of the tree and be able to reconstruct it from that state. But anyway, you can pickle the tree mesh object and it works. So the big things then, I think, as far as reproducing the mesh, as far as reproducing the current tree mesh implementation, is finishing up the plot slice command and then integrating properties, like the properties objects and the serialization from that module. And it's something that I'm not as familiar with because I just haven't used it as much. A lot of the static typing that we get from the properties object or the strong typing of objects happens in the Python file by default because those things are statically typed. So there's a few things that I just trying to understand where the properties comes into this. I'm not as familiar with that. So if somebody else who had a better understanding of the properties class could look at it and help me figure out what I need to implement to make it compatible with those save, load, copy functions that you get to find from that would be helpful.
I can take a look and try and jump in there a bit. In a lot of ways, it might not be that we actually even need to inject properties in this case, because as you said, a lot of the stuff is already strongly typed. I mean, there might be some small validation things and things like that that would be helpful, but that may or may not be necessary. It might just be the case that we actually want like a layer that lets us treat it like properties in the saving and loading, but doesn't actually implement it. So that'll take some digging, but we can see.
That's, like I said, again, that's something that I have not had that much experience with, so I just hadn't implemented it because I didn't know where it was or what to do. So it's just, we need some, I'd like to have a little bit of conversation at some point in the future about which things should be changed, which things should be made public, which things should be private, naming of, a lot of naming conventions and things that we want to stick to. I want to bring the cellgrad stuff. So right here, it's defined in the Python wrapper to the Python class. I don't think I ever said why I had to write this wrapper like this. It's because I cannot inherit from Python classes. I cannot, a C-defined Python class cannot inherit from Python classes. So that requires a little bit of a small wrapper class, essentially. The other thing we need to discuss is, eventually, is where we want the documentation of this object to live and how we want to document it. If we just want to leave this as a small wrapper and just implement everything in the underlying tree mesh and then have all the documentation live there. Just list all the documentation for everything that this tree mesh defines here. Just a few little things. And then yeah, I want to implement the cellgrad operator inside the Python class, which because all the cells know their neighbors, it shouldn't be that hard to work out. It'll be pretty similar to the logic behind the cellgrad stencil that I already have transferred. Can't really think of too many other things, unless you guys have any other questions. So there's a lot of stuff here, and you can look through it on the GitHub repository. Make comments on all the files. If you have a question like, oh, what is this line doing? Then I can go in and comment directly on that. In general, it's just a lot of things have been moved from Python to C++. I had implemented a Python version of the tree C++ file, and it was about maybe 10 times faster than the current Python implementation. So at that point, I was just realized I could do it all in C++ and just focus on that. So it was so hopefully it works for you guys. And if you have any issues, let me know, and we can hopefully debug it as quick as possible.
Yeah, man, we'll go full force right away. I mean, it's going to be huge for us to be able to use the tree mesh shells.
Yeah, yeah. Yeah, we'll make some example. Pretty excited.
Thanks a lot. Great work.
Sure.
Yeah. Sorry, I've just been kind of babbling.
Oh, this is very exciting, Joe.
I'm just like, oh, it's been like an hour and 20 minutes of me just talking.
No, thanks for the tour. It's helpful to get our heads into what you've been up to and sort of get a conceptual understanding of how things are working before like seriously diving into the code and being able to make comments on the pull request and all of that.
Yeah, and then on pull request, like I said, I made sure everything was working that I could. It builds on all the platforms for Windows. It passed all the AppBear tests. It passed all the Travis's tests. Yeah, I guess Discretize was failing on AppBear before, but
yeah, I think it was just timing out before we had too much running.
Yeah, so the tests, like I think I mentioned on the tests are about, they take 20 seconds now instead of 3 minutes.
Yeah.
That's great.
You're the boss.
Have fun.
Yeah.
Hope I didn't make you guys run over any other meeting. I have no idea.
I think that's great.
This is priority, man.
Yeah,
priority.
yeah. I think, Joe, this is a pretty big kind of for us because I don't know, like we can actually run large scale simulation and inversion with this. So that's really exciting because like current SimPEG wasn't set up for that. Yeah.
It just hopefully makes it, you can run larger tree mesh stuff now. That's what I was focusing on, right? And the tree mesh object is great for things once you have all the operators. But it was just taking too long to build them.
Yeah, which is a big hurdle. Was a big hurdle.
Yeah.
But it seems like now you fixed it, so that's great.
Like for model decomposition, it'll be perfect, right? Because now each small operator is.
Right. So there's a lot of I think there's a lot of exciting things that we could do now. Like for instance, like 3D airborne inversion, like airborne inversion for large scale. I think that with the current Octree code, I think we can actually think about doing that because previous Octree version, yeah, it was just too slow and I didn't want to jump in. But I think it seems like now we're set up because of your work. And 3D DC Octree code, and there are a lot of things that we wanted to do, but we just, we didn't have a setup. But now it seems like we have. So yeah, it'll be great to jump in and actually use it.
You'll get mentions in our theses.
Okay.
Cool.
Well,
All right.
we get Liz is doing a comp defense at 1 o'clock, so I should go help her prepare for that.
Fair enough. Well, thanks for your time, Joe.
Sure thing.
Hello, Joe.
Bye, guys.
See you on Guild.
See ya.
Yo.
Bye, Lizzie.
See ya.
Bye, and see you.